Hello community, so great that you are back. Today we talk about a new paradox that we discovered, an entropy paradox in artificial intelligence, and this will open up something beautiful. We have now a new entropy collapse that we detect, especially in reinforcement learning of our LLMs when we do advanced reasoning. What does this tell us? This tells us there is a new scaling law that we discovered. So no, there is no wall in sight, because we will talk about a new covariance here in the entropy within artificial intelligence. Now let's talk about, before we talk about the entropy collapse, what is entropy? And in my last video I already talked about an entropy probability distribution, and a lot of my viewers responded and say, hey, what do you mean with entropy? Is this the uncertainty that we see in AI? If, for example, the NVIDIA CEO says something, or is it because the Anthropic CEO tells something like massive unemployment in less than 5 years because of AI? No, nothing at all. It is also not a third, if you want, perspective here that is all part of an AI hype machine. No, listen, all those CEOs here that they act now as AI truth tellers here, they predict the future, but you know what they are. Their function is as a CEO also of a salesman. So those people are trying to sell you their products. And yes, they have here different emotional triggers. There's this phenomenon that you are left behind if you do not invest immediately in AI in their products, you know. Yes, this is a phenomenon I'm not addressing at all if I talk about entropy. If I talk about entropy, it is also not an human-ignited chaos. No, this is just here that the social media is trying to influence you. You have here priming. They have here emotional triggers for you. I'm not talking about this. Interestingly, there are some questions by my viewers said, hey, but there is a counterforce to entropy in physics, no? Because we do have stable atoms, and maybe we have even a stable proton. Also, given the lifetime of the universe of some 100 billion years, maybe it will not be as stable. Yeah, exactly. We always have here a force and a counterforce. Great idea. Yes, more publication for you to read, but what is entropy in AI before we have a look at the collapse and the new scaling laws? Now, entropy in AI is beautifully explained here in this paper 2 days ago, published here by Shanghai AI Laboratory in Tsinghua University, May 28, 2025. And the entropy mechanism of reinforcement learning for reasoning language model, like the update of the R1 model from Deepseek or the O3 model from OpenAI. And they say, hey, we found a way to overcome a major obstacle in reinforcement learning for reasoning with those LLMs, namely the collapse of a policy entropy. So you see, the entropy term is suddenly narrowed down here to the policy entropy within reinforcement learning of reasoning language model in AI. And this is the topic of today's video. Now, to give you a simple explanation, what is entropy in AI? It is kind of a control knob, you know? You can turn it up or down how curious or how cautious your AI agent will behave in a particular scenario. So this is it. If you're a little bit more into math, you said, hey, no problem. We have Shannon entropy of a probability distribution. This is also the case here. We have a policy distribution over the action given here a particular state as that the system is in. And this is here the basis of reinforcement learning. So what it does, it simply quantifies the uncertainty, or you can call it the randomness in an agent choice about the next action. So if you have a decision process of your particular agent that has a thinking core of an LLM inside, and the next challenge is, what is the next action given my particular state that I'm in? This is exactly that we need randomness. Why? Imagine all LLMs would have only one way to solve a particular problem. Everybody would do the same. It would be absolutely predictable. We would find out nothing new. We will always stick with the same old pattern. It would be boring, and there would be no competition, and there would be no advantages. Yeah, if you want to know more about the terms, this is easy. The probability that the policy pi takes here an action A when it is in this particular state S, we sum, of course, over all possible actions A that the system is theoretically able of. We have the logarithm here of the probability. This comes from information theory, never mind. And we compute here the expected, if you want, surprise the information content of the action, which is exactly what entropy kind of measures, Shannon entropy. If you would like to have a little bit more of a deep dive into AI mathematics, I have this particular video prepared for you already. So, what is now the effect? Very easy. If the policy is uncertain, the policy of our particular trained reinforcement learning is uncertain, and assigns, let's say, equal probability to, let's say, 4 different actions, so that it's not deciding, hey, this is the best way, but everything is getting the same probability, the entropy is high. The system doesn't know what to do. But if the policy is confident and picks here the same action for, let's say, one particular choice and 0 for all the others, the entropy is low. We have no randomness. The policy, the LLM, the agent decided this is the best way to do. So you see, it's relatively easy. Entropy helps an agent explore more during the learning. A higher entropy means more action variety within the decision space for this particular agent. This means we have a better exploration of new areas, maybe in the vector space that you are exploring here with your terms. And if we have a lower entropy, this means we are more focused on the best known familiar actions. We have an exploitation more of the old same stuff. The main papers of today, I've chosen here 2 papers because at first glance they contradict each other, and this is something beautiful. So we have here the first paper I already showed you, but the second paper is now more than a week old, and you say, hey, a week old paper? Yes, because I was waiting for something here to happen. Anyway, it is about the University of Illinois. It is about the unreasonable effectiveness of entropy minimization in LLM reasoning. So you see, both papers are exactly here, reasoning in LLMs and unreasonable effectiveness, entropy minimization, and the entropy mechanism. And they also work here with entropy minimalization, but from different perspective. Have a look at this. Well, you might say, is entropy a special kind of your hobby right now, or is it really important? Now I would like to show you some other paper, also from May 29, from yesterday, 2025. We have here, for example, University of Montreal, stochastic gradient descent here as a free energy minimization, a thermodynamic view of neural network training, and they say minimize the free energy function from one of my last video, balancing here the training loss and the entropy of the weight distribution. So a very interesting method. Same date, May 29, we have here on policy reinforcement learning from Microsoft Research with an optimal reward baseline. And they say, hey, we want to find here a new reinforcement learning policy. And we have the idea here of an on-policy reinforcement learning with a new baseline. Instead of DOPO, they call it here OPO. And they have here a higher output entropy. This is what characterizes the system. So you see Microsoft is doing it. Then we have here UC Berkeley and Carnegie Mellon University. They also from yesterday, bigger regularized categorical high capacity value function in reinforcement learning. Remember, PPO are efficient multitask learner, and they have here the models via a cross entropy trained, or you go here to robotics, and this is also from yesterday, communication constrained multi-robotic entropy field-based exploration. Yes, guess what? Beautifully. One really interesting paper, this is a little bit older now, a week old. This is highly interesting because it analyzes the entropy on a perspective now from test time adaptation. So this is absolutely fascinating, but maybe I can kind of summarize it at the end of this video. But at first we have to go here to our entropy and the entropy collapse. So let's start now officially, and we have here the very first paper that I showed you that I was waiting already for a week. Entropy minimization. What is it? It trains you the model to concentrate even more probability mass on the most confident outputs. So you tell the model, hey, come on, be more confident, trust yourself. The AI will tell you, hey, listen, I'm a pattern recognition machine. What do you want from me? So they have 3 new ideas they implemented and measured. So what it is, they implement here now the entropy minimization for the fine-tuning, the entropy minimization for the reinforcement learning, and the entropy minimization for inference time computation. So highly interesting that you can go more or less on all training methodologies that we know. And you might ask, so what is the outcome? What did they achieve? Now, for the first one here, surprisingly strong performance on mathematical and coding tasks, and it can even outperform here labeled GRPO training data. So this would be interesting. Reinforcement learning, they take here QN7B, without any labeled data achieves a better performance than a strong reinforcement baseline such as GRPO with 60,000 labeled examples. How is this possible? That it is better than a GRPO process with new data, new training data, 60,000 new examples. And for inference timing, they say, yeah, it matches the 32 billion QN matches here, or even exceeds the performance of the huge model like a GPT-4 Omni from OpenAI. So absolutely fascinating. Now, what is the main idea that they have? They say, if you do not train nothing, so where does it come from? And they tell us here LLM possess here some previously underappreciated reasoning capabilities that can be effectively elicited through some entropy minimization. So the idea is, hey, your system can do more than you were told. There is some hidden treasure in your system. We don't have to apply a new training step with new training data. We just take the entropy control knob and we reduce the entropy a little bit, so we have an entropy minimization in a particular way, and then the system kind of trusts itself a little bit more to provide the correct answer. So this is the benefit that we get. We just say to the system, hey, come down from your high level that you have been up-tuned here to be secure, to don't give any wrong answer, to be here within some strict limits here of your guardrails. And we say, hey, if we turn down the entropy, maybe you still know it. There were some paper before you should read this, maybe reasoning with reinforced fine-tuning, because particular in the supervised fine-tuning, they use here part of this reinforced fine-tuning. Yeah, the warm-up, you have supervised fine-tuning, and then it applies an online reinforcement learning, the PBO algorithm, with an abundance of reasoning path. Beautiful. And this is more or less what you start with here in this EM fine-tuning. So you have an unsupervised fine-tuning, directly minimizing here the token level entropy. This mirrors here supervised fine-tuning and minimizes here at the token level loss on unlabeled output sample from the model condition on the input prompts. However, they say, hey, watch out because it's difficult. The older model, especially a Llama 3.18b model, is not as good on this task. There is no hidden treasure to be found because this is more or less running here on optimal performance because it is rather old and not so good trained. But those newer models like a QN 2.5, unfortunately, they did not train on the QN 3. The 2.5, there's still some, some wiggle room left. We can go in, we can fine-tune a little bit, like when you fine-tune your car for a little bit more performance. There's still some resources left here, so they recommend here QN 2.5, especially for mathematical reasoning tasks. Yeah, simple idea, trajectory level entropy estimator, but you should remember minimizing the trajectory entropy leads to policy with a lower entropy over those trajectories, whereas minimizing here the token level entropy leads to policy with a low entropy at each single step that you generate the next token. Token or action level entropy estimator is this one. So you know this because our token level estimate is commonly used in the maximum entropy regularized RL frameworks such as the soft actor critique framework due to its low variance. And yes, this is exactly what I showed you in one of my last videos where we're looking forward to future algorithms in AI. I talked to you about the maximum entropy reinforcement learning where we have an entropy bonus added here. And yeah, let's start here at 24 minutes here into the video. And then the rest of the video I explain you here through the development path. So this was the first, this was here the entropy minimization fine-tuning. You minimize here token level entropy for those outputs. It's rather straightforward. Then you can do the same here, entropy minimization on the reinforcement learning. Here it is rather easy. Your sole reward signal is the negative entropy of the generated trajectory. I just showed you the formula for this. And if we go then to inference time, test time compute, you reduce the entropy of the next token's probability distribution before you sample, and I'll show you more about this in a second. Now, unfortunately, the GitHub repo here has only a read mode file, and I was waiting now for a week. The code to be released soon. I was waiting now for a week. There's no code as I publish here or record this video. So I'm a little bit disappointed because I cannot access this here and try it out myself. Not so good. So let's forget about this particular paper. Also, the idea is fascinating. That we still have some performance left in our LLMs we can squeeze out at no cost, no training, no additional whatsoever. We just have to do a little bit of an entropy minimization to the system. Okay, but the real beautiful main paper of today is here, the entropy mechanism of RL in the reasoning models. Here we have a complete, we check at the beginning is the GitHub here, entropy mechanism of RL, they go here. They show here the recipes, they give you here all the particular formulas, they go here with a DAPO open source implementation, they tell you exactly how to do it. Real nice, they have here the models, everything is available for you. If you ask, what is this? I have a particular video where I show you a development here, especially based on Deepseek GRPO, Group Relative Policy Optimization, to DAPO, and then I also showed you the very next step, WAPO. But they implement here this step of DAPO, so there is here for chain of thought reasoning, advanced chain of thought reasoning, here the DAPO mechanism explained to you in this particular video. So what happens now in this study? Now, finally, the video starts at, 3-4 minutes in. The question is, does reinforcement learning for LLM just trade entropy for performance? What is the relation between those two paths? And I say, okay, so let's have here a validation accuracy of a particular LLM. So we have here in green the test accuracy, you see. We have here the steps on the x-axis. So the test accuracy goes up, and then, let's say here, we just have a plateau. Over all this, we just have maximum of 5% improvement, so it plateaus out. No further improvement. What happens at the same time if we look at the training entropy of the system? Now, if we calculate the entropy, you see, okay, we have a high entropy at the beginning, we have all the ways open to us, we have all solution paths open, unexplored, but look what happens. We breaks down, we fall down here, and we are, my goodness, here, almost completely reduced, and then we just have, also if you want, kind of plateauing out. Here, all of this, here we just have some very small variation, almost nothing is happening. So within the very first steps here, everything is happening. This is not what we want. We don't want a system that says, hey, in the first 500 steps, I just decide on all possible reasoning paths for one, and then even if you continue on the training, I don't change at all. Because my physical system tells me, hey, it's not worth it. So something is happening here that's not okay. Look at here the entropy on the x-axis. Now you see we saturate. We immediately saturate here. You have the Q1 2.5 model family from the 32B down to the 0.5B. All models saturate almost immediately. So we are missing out. We are training those models on thousands and thousands of steps, and all unnecessary because the main decision path is decided here at the very first steps, and then it's just plateauing out. This is not good. This is what we call here an entropy collapse. Now, if we look at this, these are simple formulas. You just put this here into a solver, a mathematical solver, say, hey, give me here define the function, and the function is simply this one here. So the performance that we encounter here is simply an exponential function of the entropy plus some factors. This is it. Finished. We can explain the dynamic of the system. Now, we know from Sutton in 1988 that the core challenge in reinforcement learning is this delicate balance between an exploitation and an exploration of new areas. So, quantitatively, the authors tell us we further reveal that without an entropy intervention, like maybe we can do something with the entropy loss, or we can optimize the Kullback-Leibler regularization, the downstream performance is fully predictable from the policy entropy. And the fitted mathematical form function, the curve, is a simple exponential function of the entropy. So you say, interesting. So if we have this kind of collapse, we found a mathematical formula to explain this. Great. But we want a different solution, eh? Because if I just go on with more like this, if we scale now the training compute time for reinforcement learning, the result is marginal. There's nothing happening here. And even if you go to 20,000 steps, you will plateau out. So, what to do? Yeah, and they examined this here for the QN family, for the Mistral model family, for the Llama families, for the Deepseek model family. They did this here on mathematical task, and they did here the same policy entropy calculation on the coding task, and they always found here the same saturation. So this is not model specific, this is not model size specific, this is just a general thing that happens whenever we use reinforcement learning. This is here the policy entropy collapses here. Why? Why does this happen? And I know a lot of my viewers want the immediate answer. And the immediate answer is because of the softmax policy that implement in LLMs, the entropy change between two consecutive steps is proportional to the covariance of the log probability and the correspondent log change for a particular action. This is the explanation. If you say, hey, can you make it a little bit more complicated? Well, of course I can. This is here a paper that I found, unfortunately, for me in simplified Chinese. And this is, as far as I can tell, here from Sky Down Akai here, a PhD thesis on reinforcement learning theory on the internet. And here was the first time that, mathematics is universal. Never mind, if you don't speak the language, you have mathematics. And I said, hey, this is now an interesting deduction what came up with here with a covariant here. And moments later I recognized, I do have a multilingual browser, so okay, do bad, I learned from my mistakes. So this is here why the reinforcement learning policy entropy converges in the iteration. A beautiful PhD thesis has not been published yet on any archive server, but the insights we're gonna use for our understanding. There's an entropy dynamics. Try to make it simple and explain it in simple terms. There's an entropy dynamics, and this demonstrates that a high covariance is detrimental to a scalable reinforcement learning, which provides us with guidelines about uplifting policy entropy, limiting the step size of a high covariance token. So what they say, hey, what options do we have to counteract this entropy collapse? Now, if they say we want to control now the entropy, what we can do? And they say, look, we have a look at PPO and we see there are two factors that we can have a modifier. We have the clip and we have the Kullback-Lei Bai divergence. What about we modify those two terms and we have a clip covariant and a Kullback-Lei Bai covariant new term replacing here the classical PPOs in the loss function. And this is exactly what they did. Now, what is the effect of this and how they did it is, of course, the important point. Now, this new clip covariant selects here a small portion of tokens with a positive covariance and detaches here their gradients. And the Kullback-Lei Bai covariant, on the other hand, applies here a particular Kullback-Lei Bai penalty on token with the largest covariance. This is a beautiful way to actively control here the policy entropy by tuning here particular threshold parameters. So the policy model escapes now the low entropy trap. It escapes here a local minima. And this is now the beautiful thing that achieves here better performance on mathematical reasoning. So on the road to scale here the reinforcement learning performance with increased compute time, we want better results. We do not want saturation. Therefore, this novel path here, this higher entropy class here with an entropy minimalization is providing this to us. So, policy entropy. Beautiful formula. If you have seen one of my last video, you immediately understand it. If not, never mind. This entropy quantifies here the uncertainty level of the policy on current prompts, and it's widely adopted in maximum entropy reinforcement learning as a regularization term. Now, interestingly, we have correlation. And the authors tell us we obtain here the insight that a strong positive correlation between the action probability, P, on action, under the current policy and the corresponding advantage value, A, that I showed you in my last video, leads to a decrease in policy entropy. And, controversially, a negative correlation tends to increase the entropy. So they say this is interesting. So if we found this correlation between these two terms, we know now how to decrease the policy entropy, and this is here exactly what we want, a policy entropy minimalization topic. Now there's a right way and a wrong way to do it. Let's start here with the wrong way. So classical common approach here in the literature is to control the policy entropy is here to apply here correction factors to the entropy loss function itself. They did this and they had, it's kind of working. Look, here this is the entropy on the y-axis and the number of steps on the x-axis. And you see compared here to the original, this is in green line here where the entropy really collapses immediately and saturates out. We have now with these new Kullback-Leibler coefficients in the loss function that we insert there, we have a better performance. This is this kind of blue lines here. So it does not collapse immediately. It kind of holds on here to a particular entropy level. So we do have this uncertainty and we do have this potential to find new waves, new solution. We have this little bit of chaos, this little bit of wiggle room to find new solution. But sadly, if we look now at the accuracy and we validate the accuracy of those systems that have this new potential finding new ways, you see the performance now in blue is below the one in green. So we do not achieve the result. We achieve here part-time result, but the end result is not what we want. So in the end, we have a degradation in the performance indicators. So it is not the way here, adding here Kullback-Leibler penalty in the classical way. So what is the right way to do it? Well, the right way to do it, you're not going to believe it, is follow here the classical PPO optimization and suppress the tokens with high covariance. It sounds so easy, but it's interesting. You have to find this. So here we observe that if you look at all the different tokens, and we have here Q1 2.5, a 7B here, and you look here at the covariance distribution. So you have a lot of tokens that are behaving here in the mean value really beautifully, but there is a little tiny fraction, 0.02%, that are complete outliers. Look at this. So, and they tell us now, hey, a small portion of tokens, those were, exhibit some extreme high covariance, far exceeding the average. So this is saying that this outlier token take a dominant part in triggering here the entropy collapse. So we know now which token trigger the collapse. So we take care about this token. No? So at first, there's a lot of mathematics in the original paper and especially in the annex. I just give you the result. If you want to read it, it's beautiful. You have a look at the paper. So the token-wise centered cross product between the log probability and the advantage function here is here now defined. And we have here our covariant. Plus, if we deduct now here, we have now the clip covariant and the Kullback-Leibler covariant formulation, as you can see here. Rather simple explanation. They even give you here, this is now the pseudocode, the code if you want, what you have to do. If you compute here the policy loss, you notice in green is here the new formula that you substitute here, the classical red formula. So it is really beautiful, simple code. If you understand what you're doing and why you're doing, you found a new methodology. So what is the result? Let's look at the entropy dynamics now with this new correct way of modifying here and try to prevent the entropy collapse. And here you have on top the 7B model and here you have the 30B model. And you see, let's look at the 30B model. If we look at the entropy, yes, in green you have the original collapse, but now with different methods, you see we don't collapse, we don't saturate out here at the end, But there is now something beautiful. We have left a little bit of this beautiful uncertainty, of this beautiful chaos that we need to break out of the box and find new solution. Unseen, unheard solution. Have this chaos and explore it. Now there are three methods, and I've shown you here the Kullback-Leibler covariant, the Clip covariant, but there's also a method here, it's called Clip higher. Now, Clip, this is, I want to show you this in a minute. Clip higher. GRPO, Group Relative Policy Optimization with Clip higher. This, it tunes the upper threshold epsilon and a PPO loss to 0.28. This is here directly from the paper of DAPO. This is here the version 2 from May 20, 2025 from ByteDance Seed. And they have here DAPO. We already talked about this in one of my older videos. And there they developed especially this methodology, GRPO with Clip higher. So they took it here from this publication. And then we have here the final benchmark data. Now, we have here the QN 2.57 and the QN 2.532B. For those models, we have now a lot of benchmark, AIM24, AIM25, AMC, MAT500, OmniMat, Olympia Bench, Minerva, and the average. Great. And now for GRPO, they give us here this Clip higher I just showed you. And then our new two methods that we discovered just minutes ago, Clip covariant and Kullback-Leibler covariant. Have a look at this. They color this here, so you see the bold is here the best performance. So either it's Clip covariant or Kullback-Leibler covariant. One of those models outperforms here all the other performance, and you see here for AIM25, a pure GRPO gives you here 16%. If you do it with Clip high, you have 22%. This is real close to the Clip covariant, 22.7. But if you go with a Kullback-Leibler covariant, then you achieve 30, let's say, %. So you see, given your particular benchmark, you really have a real nice performance. On Olympia Bench, it is different than you have with Clip covariant here, a better performance than with the Kullback-Leibler covariants. Okay, so they tell us here, these are the detailed results here on for AIM and AMC. The results are average at 32. Well, not perfect, but okay. So what is their final result? They say our new two methods here lead here to substantial gains on the larger QN 2.532B especially. I think the same might be true for the QN 3 model. And they say our method achieves improvement up to 15% compared to GRPO on AIM24 and AIM25 respectively. And they say, hey, we found a 32B model has a greater potential for this prohibition of the entropy collapse because this model has a greater potential here from their pre-training data structure compared to the much smaller 7B model. So again, we have here another indicator. A 7B model is something beautiful, and if you have only a limited compute infrastructure, an old NVIDIA GPU, a consumer GPU, I know that you are limited to the smaller size of model. But if you want to utilize here this new scaling, these new methods, well, you have to have a bigger model that has more potential and that is able really to, to accumulate the benefits of this new methodology. And the smaller models are not really the best choice for them. As I told you, there's a lot of mathematical deduction, and this here is especially here from the PhD that I showed you here. So if you want to have a deep dive into the deduction, how they arrived at the results that I showed you, highly recommend you the PhD thesis of our colleagues. And as you know, at the end of the video, I always give you here the original conclusion here. This is a screenshot from the study. And the authors tell us, hey, we address here the challenges of the policy entropy collapse in reinforcement learning for large model reasoning. We demonstrate the performance gains are often achieved by sacrificing here the exploratory capacity, which in turn imposes a limit on improvement. So to gain a deeper understanding, they conduct a theoretical investigation into the entropy dynamics, and they found two simple regularization techniques, Clip covariance and Kullback-Leibler covariance. to directly manage the high covariance tokens and thereby counteract the entropy collapse. Looking further, reinforcement learning has been identified as the next scaling axis after the pre-training. Yes, absolutely agree. Reinforcement learning has a lot of potential here for further improving the performance of our language model. However, scaling computing for reinforcement learning requires more than an entropy minimization, and they hope further research could provide valuable insights into the role of entropy fostering reinforcement learning to reach higher level of intelligence. So you see, we found a new factor, we found a new scale, entropy, in the training of our large language model, of our reasoning models. And this is so interesting because if you think here, entropy is just this equilibrium, no? As I told you, you have in physics this entropy force, but you also have stability islands, gravitational stability islands. Or if you just look at the atom, quantum field stability islands that counteract here this force. And if you want here in artificial intelligence, we have kind of the same. No? We have an entropy collapse that we know how to prevent this and establish again this beautiful equilibrium between exploitation, having one solution that we know that works, and now we only look at one solution and try to optimize this one solution. But there's in this equilibrium also the other part, that we have resources free to go new ways, discover complete new areas in our mathematical spaces, new solution, new manifolds. Just say, hey, today I explore here unseen territories. Maybe there is a better solution to the given task. I really love this study. If you really want to understand it, it's a little bit heavy on the mathematical side, but I hope I've given you the result and explained it in a way that really opens up here and you say, hey, entropy in reinforcement learning is really something I should look out for in the very near future. And yeah, if you'd like to see more kind of this video, why not subscribe? And I see you in one of my next videos.